So welcome back for the final lecture of this week. So we are talking about different LDA variants and what are their applications. And we talked about 3 different variations like correlated topic models, dynamic topic models and supervised topic models. And we saw how they can model different assumptions. They can also be used to pair the response as a observation inside the model to make nicer topic models. So we will now see in this lecture we will also see 2 other variants. So one is called relational topic models, another is some sort of non-parametric Bayesian models, and we will see what sort of applications they can be used for. So what is the idea of relational topic models? So when you are talking about data, so many a times this is simple text data, so where they are not related to each other. Sometimes this is like a network also, so where different observations or different data points are connected together by some sort of graph structure. So for example, think about the scientific articles. So as such, you can think of them as separate different articles. Okay, this is one document, another document, different observations. You can fit a topic model there, or you can think of this as these are documents that are also connected. What is the connection between the scientific documents? With the citation network, one paper might cite another paper. Okay, so if a paper is citing another paper, there is a link between them. So you are seeing these observations are also connected. Similarly, think about the web page. One web page might give a hyperlink to another web page. So again, these are observations that are connected. Then you can talk about friends. They are connected friends in a social network profile. With the profile is kind of the document, and the connection is like the and you are trying to model the connection. So now what we are seeing here, that can we adapt our LDA model such that it can take care of not only the content but also of this link. That is, also content and connection both can this be handled by the topic models. And that's where you have this variation called relational topic models or RTMs. So relational topic models try to take care of this variation, that I have the content as well as the connection. Now, so before going to the model, how we will try to do that? Suppose we did not have these relational topic models. What we are trying to predict here, I have this whole set of observations. Now, which 2 observations will be connected to each other? So, or let us say I am talking about the scientific articles. When a person is writing a new article, what are the papers he will cite? How will I model this? So I will think of it as a learning problem. I will say, okay, I have a data set. I know there are a lot of papers, and some papers are citing other papers. Okay, so I will say, okay, I have observations, document D1, D2, D3, and so on, Dn. I know D3 is citing D2. I know Dn is citing D3, Dn is citing D1, so on. I have these observations, right? And I want to find out when a new paper Dn plus 1 comes in, what will it cite? How will I solve this problem? Suppose using LDA. What I will do, I will first run an LDA over this corpus, and I will find out, okay, this topic distributions, theta D1, theta D2, up to theta Dn. Okay, I find that out. Then I try to model, okay, given that this is theta D2, theta D3, will they link together, or whether D3 will link to D2. How will I model this? Again, you can use your regression here, right? So you can say, okay, given theta D3 and theta D2, predict the link. Yes or no? So I have some positive examples wherever there is link, and negative example wherever there is no link. At runtime, when I get a new document using LDA, I get theta D n plus 1. Now I try to combine it with D1 to Dn, find out which one it is more likely to link to. That is one way it can be handled. Now, does that remind you of something? So that will remind you of the last topic that we discussed, that was supervised LDA. Remember, there also we had the same problem. We said, okay, each document has a response. So each document might have a response R1, R2, and so on. So we said, okay, one way could be take theta D1 and run a regression from theta d1 to R1, theta d2 to R2. That was one possibility, LDA plus regression. But we said we can do something smarter than that. That is, we take it as an observation within my model. And we say, okay, with each document with Z, you are also sampling your response variable with some eta and sigma. Now, can we use the same idea in this relation topic models also? So, right now the difference is that we are working with the pairs. Okay. So, what we can do here, we can say that I have document D1, I have document D2. Now, this will have some Z, this will have some Z. Now, can I model whether they will link to each other given their individual topics, and this can now be an observation inside my model. Okay. So, this is the idea. This is a simple and direct extension of the supervised LDA, that can I now use the pairs and model the response as my another observation, model the connection as my another observation. So, this is how it is done. So, you are having the same topic models, same model for beta k, the topic probabilities over different observations, but now you look at different pairs. So, let us look at these pairs, document di and dj. So, they have theta and theta j variable. So, what we are modeling, given the z in and z jn, their individual topic probabilities, whether they will link to each other. So, that is per pair there is a binary link variable, and this is like analogous to what we did in the case of supervised topic models, which is eta times this into this, okay, plus some variance. And so, this can also allow prediction about new and unlinked data. So, how is it actually? So, what are the examples for how it will be used? So, something like this. Suppose I have a top paper, Markov chain, Monte Carlo convergence diagnostics, a comparative review. So, and I want to find out what are the other papers it will link to, or I can say, okay, suppose I am reading this paper, what are the other papers that are relevant to it, like a recommendation problem. So, I can use this idea that what is the other papers that it will link to with my RTM model. So, here are some examples that this is what your RTM model gives, and these are actually important papers that this document actually linked to. So, RTM in general can allow for prediction that given a document with new words, what are the document will link to. Okay, this is one thing that can be done. Also, suppose you give a link that this document gives links to another document, what will be the approximate distribution of that document, that also can be found using my RTM model. So, links given the new words of a document and words given the links of a new document, both can be handled. So, coming back to the model, so this formulation what it ensures is that the same latent topic assignment is used to generate the content of the document, and it also generates their linkage structure. So, you are not separately learning the linkage structure, you are learning it at the same time when you are learning your topic distributions. So, that is interesting in this RTM model. So, from the ZIN and ZJN, you are trying to predict what will be your YIJ. Okay. Now, here is one problem. So, this is your simple model. So, this is what your LDA model is. Draw your topic proportions, then for each word draw the topic assignment and draw the word. Okay. Now, for the relational part, for each pair document D and D prime, what you are doing? You are trying to sample the variable y, whether they will link or not, and this depends on their ZD and ZD prime. And what is the function? It is a psi of given ZD and ZD prime, and this is modeled like this. This is as in exponential function over eta transpose a Hadamard product over ZD and ZD prime. Now, what do I mean by that? So, remember in the supervised LDA model also we did eta transpose Z bar, right, and this gave me a scalar. Two vectors you are multiplying, they is giving you a scalar, they have the same dimensions. Right now, here also you have eta transpose, same dimension as the number of topics, and you are multiplying it with Z d bar head element product with ZD prime var. Now what are ZD and ZD prime? ZD is what are the topic probability is document D, okay, and this is in document D prime. Again they are vectors. Head element product is nothing but element wise product. So you multiply this element with this element with this element, and so on, and then you add it and multiply with eta transpose. So this will again give you a scalar, okay, and plus you might add some sort of bias or variance. This is a bias here. So ZD is nothing but the topic probabilities in each document. Use it for the pair and get a head element product approach, and plus a bias term gives you, okay, whether the document is likely to these two pairs are likely to link or not, right? Eta transpose and this total thing. And in their paper they also use the sigmoid function apart from the exponential function. And link function models each per pair binary variable as a logistic regression, and this is by eta and nu. Okay. So so this is your relation topic model. What is one problem with this model? So for each pair of documents you have to define their response, that is whether they are linking together or not. So why D1, D2, is it 1 or 0? Whenever a document is giving a link to another document, you can always write a 1. But whenever a document is not giving a link to another document, it is not necessary that they are not related at all. It may be that he is not giving the link, or the link might occur in future. There are many other things depending on the data points. So one thing is that whenever there is a link, you take it as 1. Whenever there is no link, you take it as an unobserved variable. So I do not know if there is a link or not. So that also helps you in being computationally efficient. It avoids getting you so many different pairs of documents, right? So that is especially in the case of social networks, whenever there is an absence of link, you cannot take it as if y d1 d2 is equal to 0. Example also you can see from your Facebook profile. So you are taking the profile as your documents, and you are finding out if this person will become a friend of another person. So even if they are not friends at this time, it might happen that they will become friends in future. So absence of the link cannot be taken for that the response should be 0. So it can be taken as an unobserved variable. That is a better solution. So this is done, and then so they tested whether this works better than the model of LDA plus regression. This was the first thing that we saw, that you take the topics from document D1, document T2, and learn a regression over there. That is one option. Another is you take the pair which are linking as an observed variable and also use it for learning your topics inside the model itself, and that they found gives much better performance than the LDA plus regression model for this task. Given a new document, what is the document it will link to? So these are other examples, like for this document, competitive environments evolve better solutions for complex tasks. Documents like co-evolving high-level representations were coming out to be at first position in the RTM model, but were not coming out from LDA plus regression model. So this was something interesting that they saw from this model. Now, finally, we will wrap up this week by some simple discussion on non-parametric Bayesian models. So what do we see in the case of LDA models? So in LDA, what we are having, we are defining that this corpus consists of certain topics, okay, and then each document I find out what are the topic assignment. Each word I find out what is the topic assignment for that word. So what is one problem here? I have to tell a priori how many topics that are there in the data. But that may not be an easy parameter to always give, right? You may not know, okay, should I use 10 topics, 20 topics, 100 topics in this data? So can my model itself find out what will be the number of topics as such? And that's where we come to this topic of non-parametric Bayesian. So this parameter goes away. You do not have this parameter of number of topics anymore, okay? So in many data analysis settings, we will not know what is the number of topics a priori. So, in Bayesian non-parametric models, what we assume is that so we are not fixing number of parameters, but that also means okay, my data can have any number of parameters, that means any number of topics. So, I have to start with the assumption that there are infinite number of topics, okay, and my data can take any finite number of them. So, it can take 100, 500, 30, whatever it needs. So, in general I have an infinite number of topics. So, that's what is interesting about it. It assumes that there is an infinite number of latent clusters or topics, but only a finite number of them is used to generate the observed data. But you do not give it as an input to your model how many such clusters do you need. This is what model on its own comes up when it sees the observations. So, the posterior provides a distribution over the number of clusters, the assignment of data to clusters, and the parameters with each cluster. All these are different parameters of your LDA model that can be learned from this Bayesian nonparametric model. So, we will see, so there are actually many different variations of this Bayesian nonparametric models, also known as hierarchical Dirichlet processes. Because this is a very wide topic, we will not cover this topic in detail in this course. We will just give you some intuition that how do you come up with this infinite topics, right, in your setting. So, and how does it model any finite number of topics in the data, even if you are starting with the infinite topics. So, we will talk about one particular setting, that is a Chinese restaurant process that can be used for modeling the or grouping your observation into some finite number of groups. The number is not told a priori. So, what is this process? It's quite interesting. So, this is a Chinese restaurant process. So we are talking about a restaurant. So, we are saying that suppose there is a restaurant where there are infinite number of tables. Okay, when you see here the term infinite, immediately what comes to your mind? Okay, these are the latent clusters. So, I have infinite tables in that restaurant, and then there are customers that are coming up. So, these are like observations. So, you are fitting the observations to different clusters. Now, the model says, okay, when the customers are coming in the restaurant, how are they seated on the tables? Now, one thing that it says is that the tables are of infinite capacity. So, they can each table can take as many customers as you want. So, there is no limit on the number of customers that can sit on a table. Okay. So, now how do we assign customers to the tables in this process? And that is where, so it says okay. So, I have some tables, infinite number of tables. So, customer 1 comes in and sits at the first table, okay, table 1, fine. So, customer 1 is no problem. Now the customer 2 comes in. So, idea is that customer 2 now sits on table 1 with a probability 1 divided by 1 plus alpha, and sits on a new table with a probability alpha divided by 1 plus alpha. You can see it adds up to 1. Okay. Fine. So, it can sit at either table 1 or table 2. Now, when a new customer comes in, certain point of Cn, it can sit off, suppose this table, this table, this table is occupied. It can sit either at the occupied tables or at a new table. So, what we say, it can sit on any of the occupied tables with a probability proportional to number of customers already there, okay, and on a new table with a probability proportional to alpha. So, that is, so remember that is what we did here. This is proportional to 1, this is proportional to alpha, and then we normalize, we get 1 divided by 1 plus alpha, alpha divided by 1 plus alpha. At any given a point of time, you will have certain configuration, different tables will have different number of customers. So, new customer comes in, it can sit off any other table with a probability proportional to the number of customers already there, or it can choose a new table, and that is how you can fill in any number of customers on any number of tables. So, you will see at the end of this process, you can have any number of tables, right? It is a random process. You might have 5 tables, filled, 10 tables filled, 15 tables filled. So you can have any number of clusters. This does not have to be defined a priori, right? From your sampling, you can choose any number of topics or clusters. Now, one thing, what will be the effect of the parameter alpha? Suppose your alpha is large versus alpha is small. If your alpha is large, what will happen? If alpha is large, when a customer comes in, there is a large probability that it will choose a new table. Okay? So that means with large alpha, you can get large number of topics. So this gives you some idea. Okay, if you want more number of topics and each topic having small number of observations, then you will choose a large alpha. But if you choose a smaller alpha, you will probably choose a small number of topics, because the customer will have a higher probability of sitting at any of the tables that are previously occupied. So that will be the effect of these alpha. So coming back, so first customer enters and sits at the first table. Second customer enters and sits at the first table with a probability of 1 by 1 plus alpha, and the next unoccupied table with the probability alpha divided by 1 plus alpha. And when the nth customer arrives, she sits at any of the occupied tables with a probability proportional to the number of previous customers already seated on the table, and at the next unoccupied table with the probability proportional to alpha. And that's how I can distribute all the customers in a restaurant. And we saw that if I have a large value of alpha, I'll have more occupied tables and fewer customers per table, right? So we saw that. Now, okay, this looks interesting. If I have a document, I can model. So these tables as my topics, and these words, these customers as my words. And I can say, okay, which words are assigned to what topics. But how do I model my whole corpus? You see, I can model my one, this can be thought of as my one document, D1. I know, okay, what are the topics and what are the customers. But suppose I have a corpus, right? So I generally want it for my corpus. So corpus means I will have multiple such documents. The one thing could be I fill it independently for each document. But if I do that, there is no correlation between the assignment here in D1 and D2. Okay, so it might happen D1, I have first table, some words are filling in here like government, table 2, some words like sports, something, okay, and document D2, the word sports might start coming here, and there will be no correlation between the topics here in this document, topics in this document, okay. So I cannot run this Chinese restaurant process independently for different documents. That way I will not be able to have a correlation between these. So what is actually done? So we saw that Chinese restaurant process, it helps in obtaining a random partition as a sequence of customers sitting at tables in a restaurant. So you get a random partition of words into various topics. Now we also see that tables can be thought of as topics and customers as word in the restaurant, or restaurant can be thought of as document. However, it cannot model the entire corpus. For that, we can extend CRP to a set of restaurants. So that is, can be extended to defining each document as a separate restaurant. Okay, and this is called Chinese restaurant franchise. So now we are going from Chinese restaurant process to Chinese restaurant franchise. So this franchise has a lot of restaurants, and that's why we will try to connect the different topics. So let us see how do we connect the different topics. So again, so this is what is similar to CRP. So customer in the jth restaurant sits at tables in the same manner as in CRP. Okay, so customer comes in the restaurant, any of the restaurant. Now it sees which tables are already occupied, how many customers are there, the probability proportional to the number of customers, it sits at that table, and the probability proportional to alpha, it sits at the next unoccupied table. So that remains the same as CRP. Now where is this connection among topics coming in? And that is coming in from the nice idea about the franchise, that is, let us say that there is a franchise-wide menu. So now you have the new term of menu. There is a certain dishes that are there in all the restaurants, and that is franchise-wide. So whenever a customer comes at a given table, it orders a dish from that menu. Now whoever comes in next will have the same dish. Whoever customer comes in next will share the same dish. Now this dish is shared throughout the restaurants. So now this dish at a table acts as the topic of that of the document. So you can have, so now the dishes are same across the different restaurants, and that's where you can model the same topics. So how do we achieve coupling among the restaurants? So this is achieved by a franchise-wide menu. So what we say that the first customer to sit at a table in a restaurant chooses a dish from the menu, and all the customers who are sitting at that table will share the same menu. And dishes are chosen with a probability proportional to the number of tables which already have that served that dish. So if this dish is served at many different tables across the franchise, then this will have a higher probability. So that way you are also giving a prior probability on choosing a particular dish on a given table. So it will look something like that. So what you are seeing 3 different restaurants in this franchise, 1, 2 and 3. Now this shy 1 tells for the restaurant 1 what is the dish at table 1. So this is phi 1. This is from the global menu of dishes, phi 1, phi 2 and so on. This is the global menu. The second table has phi 2, third table has phi 1. That means more than one tables can order the same dish. That is possible in that model. See why? Because you see, when a customer comes in, it will first choose the table, right? So it can either to choose one of the table that is occupied or new unoccupied table. Then when it chooses the table, it chooses one of the dishes. So that means it can, the same dish can be chosen at more than one tables. Okay, so that means this table also the same dish was chosen, and so on. Next, second restaurant, first table chose dish phi 3. Second table phi 1, third table phi 3 and so on. Okay, so it has certain different choices, and then the third restaurant, first table chose phi 1, second table chose phi 2 and so on. Now you are also seeing the customer assignments. So in this first restaurant, customers are coming in theta 1, theta 1, 2, theta 1, 3 and so on. Theta 1 sits table 1, theta 1, 2 sits at table 2, theta 1, 3 at table 1, 1, 4 at table 1, 1, 8 at table 1, 5, 6 here, 7 here and so on. So there are certain assignments that are given to these customers. Similarly here, theta 2, 1, 2, 2 sit here, and 2, 3, 2, 4, 2, 6 sit here. Now similar to LDA, what we will have from when a customer chooses a dish, it will see what the other customers have chosen. Okay, that's where they will be coupling, that the words will be assigned similar sort of topics across the different restaurants. So you are seeing each restaurant is modeled by a rectangle. Each customer are seated at the tables, and each table you are serving a dish from a global menu. So this is a table indicator. Okay, so by modeling this, now you will know that what are the assignments of your different words to different topics in all these documents. Okay, interesting thing is that you did not have to tell how many topics do you need a priori, but this the model can itself learn from the observation. So what we have seen, okay, so you have an LDA model. You can use it for very nice applications like finding out similarity between documents, words. But suppose you want to use some rich assumption like topics are correlated, changing over time, so you can modify that model. That's where it has a lot of, the model is very, very strong. It can use many different variations. Then you say, okay, this is unsupervised model, but suppose I want to model some responses with that. That is, what is the rating of this text or how many likes. I can take it as an observation variable inside response variable, and learn my topics accordingly. That is in supervised topic model. I can go further and say, okay, which two documents are connected together, that I can again measure the link as an observation. So link can be as a response or observation between two pair of documents. This was by relational topic models. And then we said, okay, suppose you do not want to use any parameters, how many topics, etc. Then you go to Bayesian nonparametrics. And there again, there are a lot of different models. We talked about very briefly about Chinese restaurant process and Chinese restaurant franchise. But there are other variations also that can be used. And depending on your application, you can choose one or the other models. And there are tools available that will allow you to model any of this. So that brings us to the end of this 9th week, where we discussed a lot about topic models and also about semantics, talk on semantics. From the next week, we will start talking about different applications. So we'll talk about entity linking, information extraction in the next week, and then we'll go about other applications in the subsequent weeks. So thank you and see you in the next week.